In our third lecture, we're going to take an overview of our planetary system. We'll get introduced to some of the major bodies in the system, and we'll hit on a few facts about them to, again, take a first look, an overview, so to speak, of that. In future lectures, then we'll be able to go into much more detail about the different bodies. Let's begin by considering that there's 5 major types of objects in our solar system that we'll be discussing. First of all, the terrestrial worlds. These include Mercury, Venus, Earth, Mars, and our moon. Now, these bodies are relatively small bodies, rocky bodies that orbit in the inner solar system. Next, we have the Jovian planets, Jupiter, Saturn, Uranus, and Neptune. These are much larger bodies, much larger planets, primarily composed of gas rather than rock, and these orbit much farther away in the outer solar system. We'll be seeing later the third type of body, and these are the large moons of the solar system. Now, while Earth does have a large moon, primarily we find these in the outer solar system around the Jovian planets. These are an amazingly diverse and fascinating group of worlds that tell us much about the processes that occur in the outer solar system. We'll be spending some time looking at small rocky bodies in the solar system that generally orbit between Mars and Jupiter. These are known as asteroids. And then we'll be looking at smaller icy bodies that orbit in the outer solar system, generally out beyond the Jovian worlds. The smallest of these are comets. These become familiar to us when they wander into the inner solar system and warm up a bit, perhaps showing us a beautiful tail. But in recent years, we've been able to not only identify, but begin to learn about some medium-sized objects, now called Kuiper Belt objects. And a few of these can actually be quite large. As we'll see, this is the planet Pluto and other objects like it. Before we go ahead and get into seeing the different bodies, getting introduced, I want to make an important point about some of the properties of the solar system as a whole. These properties are important because they're going to help us understand a lot more about the solar system. For example, its formation. How did these bodies get where they are? And why are they in the different locations? Well, these properties include things such as the way the planets all orbit the sun in the same direction. They also orbit the sun approximately in the same plane. And finally, most of the larger bodies in the solar system all rotate on their axis in the same direction. Now, this can't just be coincidence, but rather these properties are telling us something about the different worlds in our solar system, and again, how they formed and other important information. But let's take a little closer look now at each of the terrestrial planets. You see here Mercury, Venus, Earth, Mars, and our moon. Again, I mentioned these are relatively small bodies, some thousands of miles in diameter. These generally orbit within the inner solar system, closer to the sun. Mercury is a very hot world, of course, being close to the sun. Does not have any atmosphere. It's about 1/3 the size of Earth. Heavily cratered terrain, very much like our moon. There's evidence that there were lava flows in the ancient past, but in general, a very dense planet, and we'll see the reason why. Speaking of our moon, perhaps you've looked up and seen it, and most people are familiar with the many, many craters on our moon. The moon is very much heavily cratered, and yet there are some regions that are not so heavily cratered. We kind of see those as darker areas. These are called the mare, an ancient word that meant seas. Early people thought perhaps they were seas. They're not, as again, there's no atmosphere on the moon. While in contrast to these smooth mare regions where there's few craters, the moon has higher elevation regions where they're heavily cratered, and these are simply called the highland regions. These craters were all formed long ago by numerous impacts as various bodies have crashed into the moon. Some of these impacts were large enough to generate enough heat to melt the surface and allow molten lava from within to then flow to the surface, so to speak, flood an area and fill it in, covering up the oldest craters and showing us now these mare regions. Let's move on and talk about Venus. Venus is very similar to Earth in size and rough composition. It is closer to the Sun. We would expect it to be somewhat warmer. And yet we find that Venus is far hotter than Earth. Why is that? Well, Venus is well known for its very thick carbon dioxide atmosphere. In recent years, we've learned a lot about this as a greenhouse effect. Here on Earth even, it's a milder effect. But Venus has a very thick carbon dioxide atmosphere with a surface pressure 90 times that of Earth. So not anywhere you'd want to go. This thick atmosphere creates a tremendous greenhouse effect. The temperature on the surface over 800 degrees Fahrenheit. So an extremely hostile environment. Made it very difficult for us to study Venus. In fact, because of the thick clouds, we cannot even see the surface. How have we begun to learn about it? Well, as you see in this slide, we've actually dispatched spacecraft to Venus with the equipment to map it using radar, much as we use that here on Earth. These radar beams can penetrate those clouds and give us a look at the topography, the elevation of different regions of Venus. And when we assemble that into a global map, we at least get a first picture of Venus surface. Here in the picture you see again, these are false colors, but the higher elevations here are in white. The lowest elevations are in blue. So this has given us again our first look at the surface of Venus, even though we can't see it in normal light. Later in the course, we'll see some more detailed images of later spacecraft that gave us finer information, finer detailed, higher resolution images of the surface. Well, next we come to perhaps the most beautiful and spectacular planet of all, our planet Earth. Now in our course, we won't be able to spend a lot of time on all of the vast amount of knowledge we've learned about Earth, its geological formations, its atmospheric processes, all the biology. These things could take a lifetime to study. Instead, we'll simply be able to look in this course at Earth as one of the other planets, comparing and contrasting it as well. We know, of course, Earth is unique in having 5 major oceans and our 7 major continents. And yet again, we don't want to forget that fragile atmosphere that's really vital for all life. So Earth is an amazingly complex world, but studying it in context with the other planets allows us to see it far more clearly. Moving on to Mars, you see here a few images on the right from the Hubble Space Telescope showing us Mars, and on the left an artist's impression. Mars is smaller than Earth, about half the radius, about 10% the mass, farther from the Sun than Earth is. It has a similar axis tilt, similar rotation period, so the days would be familiar to us. Mars, rather than have a very thick atmosphere, has a very thin atmosphere. So again, a very difficult environment for us, but of all the planets, perhaps the most Earth-like. You do notice some different regions. They're a little darker than others. You notice the polar caps. So Mars has intrigued scientists now for many, many decades, and in recent years, much time and effort and money has been spent to begin to explore Mars. Well, what have we found? In brief, Mars is well known for some gigantic geologic formations. Here we'll just touch on 2 of them. On the right, you see an image of Mars showing the tremendous canyon system known as Valles Marineris, 2,500 miles long. And you can see from our image here that that canyon system would stretch across the United States, dwarfing our Grand Canyon. Not only is it 2,500 miles long, but it's hundreds of miles wide in places. By far the largest canyon system we know of anywhere in the solar system. In the lower left, you see that Mars also boasts the largest volcano in the solar system, Olympus Mons, 16 miles high. That's over 3 times the height of Mount Everest, a gigantic volcano. You see from our illustration here that it would literally cover the state of Arizona. So truly an immense volcano. Why would Mars, a smaller planet, have such huge geologic formations? Well, we'll get back to that question a little bit later, but for now, let's just say it's a very different world compared to others that have such structures. Here you see an actual image from the surface of Mars. You may be aware that NASA and others have been able to land spacecraft successfully on the surface. These spacecrafts have not only given us these spectacular views, but have literally been able now to travel over the surface, different rovers, and examine the geology, helping us to understand far better the surface of Mars. You see it's a very dry environment, very rocky, very dusty, and yes, even the sky appears a different color because a little bit of that dust is lifted up into the atmosphere by Mars' weak atmosphere. So we've taken just a quick first look here at the terrestrial worlds. Again, Mercury, Venus, Earth, Mars, and our moon. And we're going to be taking an approach similar to what scientists do in studying these worlds. Rather than just look at them each individually, we're going to look at them as a group. We're going to compare and contrast different features on each one. We're going to see how different processes that are similar operate under different conditions. The methodology here is known as comparative planetology. And this allows us, again, to really see the bigger picture and get each of them in their own context. Moving on to the asteroids, we mentioned that these are smaller rocky bodies, and you see a few images of them here. These are not even large enough to have enough gravity to form themselves into a spherical shape. But asteroids are very, very important in our study of the solar system. Why is that? Because many of them have not changed very much at all since the beginning of the solar system. And as a result, these offer us pristine examples of the material from the early solar system that allows us, in a sense, to go back in time and examine the early solar system. So scientists have been very curious about these, and in recent years we've been able to send spacecraft there as well to examine them up close. We move on now to the outer solar system, the Jovian planets. And here you see Jupiter, Saturn, Uranus, and Neptune. Huge planets made of gas, many times the size of Earth. Interestingly, Saturn being well known for its rings, the other Jovian planets actually do have rings, although they're very difficult to see here from Earth. But you notice the very interesting appearance of each of these Jovian planets. Jupiter with this powerful dynamic atmosphere, Saturn with those beautiful rings. Uranus and Neptune show this very interesting bluish color. Let's see what that's about as we go along. But let's start with Jupiter. Jupiter being very, very large, 11 times the diameter of Earth. Imagine then perhaps a 1-foot diameter Earth globe. Well, we'd need an 11-foot diameter Jupiter globe to be at the correct scale. So truly a huge planet, over 300 times the mass of Earth, and Jupiter has enough volume to hold 1,000 Earths inside of it. So again, truly a huge planet. You notice the dynamic appearance of its very active atmosphere here, these dark bands and zones. Notice in the lower image, lower part of Jupiter's image, these round oval spots, some white ones there, and one large red one in particular, the Great Red Spot. These are gigantic storm systems on Jupiter that would dwarf anything here on Earth. In fact, these storms are larger than Earth. So this, of course, raises many questions. Why does Jupiter have these? How did they get there? What keeps them going for a long time? How do they change over time? All these things atmospheric scientists are very interested to study in this very, very fascinating planet, Jupiter. Saturn, of course, known for the spectacular ring system. These rings are not solid, but rather are composed of numerous, many, many millions of smaller bodies, chunks of ice, orbiting Saturn in a nice flat plane. Well, later on we'll discuss a little bit about why do they do that? How did they get there? Why do the other planets have rings, but they're not nearly so beautiful and obvious as Saturn's? You notice Saturn as a planet does not seem as active as Jupiter, although it does have some very interesting things that we'll be looking at as well. Moving on to Uranus. Uranus is very difficult to study because of its great distance from Earth. And yet in recent years, we've been able to make some improvements and use our techniques to get a better look at it. And we'll see just in a few minutes that we've actually been able to send one spacecraft to get a close-up view. What's the blue color trying to tell us? Well, very simply put, it's telling us that there is methane in Uranus' atmosphere. Methane tends to absorb certain colors of light, the red colors, and yet to reflect the blue light towards us. You notice in these two views on the left, Uranus appears somewhat quiet, but on the right you notice some bright white spots. Well, these also are huge storms in the atmosphere of Uranus, and so the point being that we do see a very changing appearance of Uranus over time. These images actually do reveal the faint thin rings of Uranus. Now again, we wouldn't normally see these with our own vision, but these are infrared pictures that scientists have taken, and in infrared the rings are far easier to see. We come then to Neptune, somewhat similar to Uranus in appearance, but even further yet, making it extremely difficult to study here from Earth. Much of what we know about Neptune comes from the Voyager 2 mission. That spacecraft visited in 1989 and gave us our best close-up views of Neptune. You see one here showing this great dark spot. Again, a huge storm system in Neptune, although we don't believe that the spot has endured this long. Neptune's blue color, again, due to the methane in its atmosphere as well. So very similar to Uranus in that respect. So we've taken a brief view here then of the Jovian planets. We've seen some interesting things. We'll be back to see them all in more detail. But before we move on, let me highlight for just a moment that the Jovian planets have very fascinating large moons. Here you see kind of a summary showing some of those. Here are the 4 large moons of Jupiter that Galileo saw in his little telescope. And yet today we have far better views from close-up spacecraft visits. Saturn has a large moon, Titan, the only moon in the solar system with an atmosphere. So it's been the subject of intense study recently. Uranus and Neptune also have some moons that are showing us a wide variety of surfaces and features, characteristics that have taught us a lot about conditions in the outer solar system. And yes, we'll be sure to take a close look at Pluto with its moon, Charon. Speaking of Pluto, you may know that in the summer of 2015, the world was thrilled to get our first close-up view of Pluto from NASA's New Horizons mission. Here we have a small icy world, approximately half rock and half ice, very thin little atmosphere, and yet here we see a few of the recent close-up images. Scientists were delighted to see a surprisingly active world. Traditional thinking might have said, well, Pluto shouldn't really be all that active geologically, and yet we were in for a very pleasant surprise. So we'll be talking more about Pluto and some of the things we've learned just recently. As I mentioned, it has one large moon, Charon, you see below it. Also a very complex, interesting world in its own right that we'll be taking a look at as well. You may have heard that in recent years there's been a little bit of a disagreement on whether Pluto should be a planet. Well, rest assured we'll be addressing that topic as well. For now, we'll just say that Pluto is obviously much smaller than the other 8 major planets. Certainly not a gas giant Jovian planet, and really it's not a terrestrial world because of the high abundance of ice, very much like a gigantic comet, so to speak. And finally, Pluto does have a very different orbit than the 8 major planets. So these are some of the reasons why scientists view Pluto as part of a different class of objects. So we'll be back later to examine that more closely. Speaking of comets, comets you may know are small icy bodies in the outer solar system, some tens of miles across. Now these generally orbit out there pretty quietly, pretty peacefully, and yet occasionally for various reasons one may fall inward towards the sun. Well, you can imagine that that ice as it approaches the sun warms up. Now it doesn't melt, but it does turn into a gas, and if the comet gets close enough to the sun we will see a tail form. So these also are very interesting objects for us to study. They gave us a view of what conditions were like in the early solar system in the outer regions. And so again, the subject of intense research today. Just in recent years, scientists have been happy to be able to explore some medium-sized icy objects, larger than comets, but smaller than planets. These are now called Kuiper Belt objects, in honor of the astronomer who first predicted their existence. Again, fairly large objects, but as you see here, nowhere near as large as Earth. Icy composition. Some of the larger ones, you may have heard the new term, are considered dwarf planets. So here we have an entirely new class of objects that scientists can study. Well, before concluding, I'd like to spend a few minutes and just explain a little bit about how we've learned so much about the solar system in recent years. For decades, even centuries, we were limited to simply looking at them with our earthbound telescopes. But in the last 50 years or so, our technologies enable us to actually send spacecraft out to visit those up close. And the results have been amazing, completely transforming our understanding of the solar system. How have we done that? Well, the first way we do that is simply to launch a spacecraft on a trajectory that it flies past a planet and takes as many pictures and other measurements as possible. And we simply call that a flyby. Now this, of course, is the least expensive type of mission, but unfortunately it means that you have the least amount of time to observe the planet that you want to. You may have heard names such as the early Pioneers and Mariner missions to the inner planets. Later, the Voyagers and even now the New Horizons mission to the outer solar system have flown past planets for the first time. Sometimes these spacecraft will actually use the gravity of one planet to adjust their trajectory to go on to another. And in this way, one spacecraft can visit several planets. Far better, when possible, is to be able to send a spacecraft out and put it into orbit around the planet you wish to study. This allows us then to monitor the planet for quite some time, watch for changes, gather more pictures, make more measurements, and really learn far more about it. You may have heard of the early Viking missions to Mars, the Magellan mission to Venus that did the mapping, the Galileo mission to Jupiter, and more recently the Mars Global Surveyor and Cassini missions. So these spacecraft are very sophisticated, very powerful tools for us to learn more about these planets. Finally, in some cases, we've actually been able to land on planets with spacecraft or perhaps drop a probe into the atmosphere of a planet. This gives us tremendous capability to explore the local surface and geology of the planet. Our earliest attempts included the Vikings to Mars. Perhaps in recent years you heard of the Spirit and Opportunity rovers that traversed far and wide over the surface of Mars. And more recently, the Huygens probe that was dropped into the atmosphere of Titan, Saturn's moon. So these have given us, again, tremendous insight into these bodies, being able to look and see them up close and learn far more than we could ever learn from Earth. So let's wrap up with a summary then of our brief overview of our planetary system. We started out by looking at the various major types of bodies in the solar system. We saw the terrestrial planets, we saw the Jovian planets, we mentioned briefly the major moons of the solar system, and we talked about smaller bodies such as asteroids, comets, and Kuiper Belt objects. We mentioned briefly that scientists generally use comparative planetology in order to study these bodies most effectively, not only looking at them individually, but stepping back to compare and contrast how different processes take place under different conditions. And then finally, we wrapped up with a brief section discussing how our spacecraft have traveled to these planets, taking close-up pictures and measurements, sometimes flying past, sometimes orbiting, sometimes even landing on these worlds. So we've come a long way in our understanding of the solar system in recent years, and we look forward now in our future lectures to learning much more in detail.